Welcome to this next lecture. We now extend our journey into machine learning for power system security by exploring two important topics: the support vector machines, or SVMs, and the performance indicators used to evaluate classification results. SVMs are widely used in security assessment because they can create clear separation boundaries between secure and insecure operating points, even in a non-linear space. At the same time, understanding how to evaluate such models is essential before deploying them in critical environments like the power system. This lecture has two learning objectives. Learning objective number one is to describe the basic principle of SVMs, how they classify security risks. The learning objective two is to describe the key performance metrics used to assess classification quality. By the end of this lecture, you will understand both how SVMs work and how to judge whether they perform well to assist operators. To motivate SVMs, let us begin with a simple question. Given two classes, secure and insecure, how do we best choose how to separate with a separating line? On this slide, you see three candidate hyperplanes. At first glance, several lines appear to separate the classes correctly. But the question is, which one generalizes the best? The SVM's approach to this problem is to maximize the margin, the distance between the separating hyperplane and the nearest data points from each class. A larger margin means the model is more robust to noise, has small variations in measurements, are less likely to cause misclassification, and the overall generalization tends to improve. This slide introduces a linear SVM in action. You see the secure, the pink, and insecure in blue data points, and the SVM has drawn a boundary between the two regions. The shaded areas illustrate the predicted class on the entire feature space. And the linear SVM tries to find the hyperplane that best separates the two classes with the maximum margin. The support vectors, the data points closest to the boundary, play a decisive role in determining the location of the hyperplane. Even in this simple example, SVMs provide a clean and interpretable boundary, which is very useful in security assessment tasks. So this slide shows the mathematical formulation behind SVMs. The decision function takes the form shown here. Based on the sign, we allocate whether we classify the sample as insecure, so as +1, or to classify it as secure with a -1. The SVM tries to position the hyperplane so that it creates the most reliable separation between the two categories. This is exactly what we want in power system security, a fast and trustworthy classifier. But what if the data cannot be separated by a straight line? This is where the kernel trick becomes essential. This trick allows SVMs to classify data that is not linearly separable by implicitly transforming it into a higher dimensional space. On the slide, we see two examples. On the left, you see the radial basis function, RBF, kernel, for an SVM. This RBF produces a smooth nonlinear boundary, and the F1 score becomes 0.8598, and the accuracy is 0.866. On the right, you see the polynomial kernel SVM. This produces a more complex, curved boundary. The F1 score there is 0.8679 and the accuracy is 0.8755. The two models achieve similar performance, but with slightly different boundaries. The key idea is that kernels let SVMs adapt to more complex structures in the data without explicitly computing higher dimensional features. Before evaluating performance, we must separate our data into training and test set. And on this slide, you see the data split is about 70% used for training and about 30% is held back for testing. This is essential because we want to know whether the model works or works not, just on the examples it has already seen, but also on new unseen data, similarly to how it will operate in real grid conditions. If a model performs well on the training data, but poorly on the test data, it is overfitting and not suitable for deployment. Now we introduce the key performance indicators that allow us to quantify how well a classifier works. The confusion matrix on this slide divides outcomes into true positives, TP, false negatives, FN, false positives, FP, and true negative, TN. Using these, we define the accuracy, which is the fraction of correct predictions, and the precision. So among the points predicted as insecure, how many truly are insecure? Then we define the recall. Among all truly insecure points, how many did the model detect? And then we define the classification error, the fraction of misclassified samples. In power system security, this can be especially important because missing an insecure state can have severe consequences. This slide shows a precision recall curve, which highlights the trade-off between the two metrics. A classifier that tries to catch every insecure point with a high recall may generate more false alarms and leading to a lower precision. Conversely, a strict classifier with high precision may miss dangerous states. The right balance depends on the operational context. In power system security, the cost of missing an insecure state is extremely high. So achieving a strong recall is often prioritized, even at the cost of some additional false alarms. To summarize, SVMs classify secure and insecure operating points by finding a separating hyperplane with a maximum margin. Using kernels, SVMs can model non-linear boundaries suited for the complexity of power system security. Evaluating a model requires proper data splitting and performance metrics like accuracy, precision, the recall, and the F1 score. Precision recall trade-offs must be considered carefully in safety-critical contexts. Together, SVMs and performance metrics provide the tools needed to build a reliable machine learning model for near real-time security assessments in the power system.